Today we have a quadrilateral ABCD, arbitrary convex quadrilateral. And what we're going to do, we're going to put circles on it. So we're going to take this blue circle and put it on a side AB, and side AB will be the diameter of the circle. In a similar fashion, we're going to take this yellow circle and make BC its diameter. Then we make CD is the diameter of another circle, and AD is the diameter of the fourth circle. And an interesting thing is going to happen. The thing is that these four circles are going to cover all the interior of this quadrilateral ABCD. And that's what we would like to prove now. The way we're going to prove it is by assuming the opposite. So we're going to assume that there is such a point P inside of this quadrilateral that is not covered by any of those four circles. And since it's not covered by any of these four circles, it's definitely not covered by this green circle. This P lays outside of the green circle. So now we're going to connect this point P with points A and D. Notice that the segment DP is outside of the circle, but the segment AP intersects the circle at point E. And really, no matter where we take this point P outside of the circle, there will be always one of those segments that intersect the circle. We will have either one of those segments or two. In this particular case, there's one. So let's connect point E and point D. And now notice that this angle E, angle DEA, is an inscribed angle. And that inscribed angle sits on a diameter AD. And that means that this angle should be 90 degrees by Thales' theorem. But now if you look at the triangle DPE, it's a right triangle. Sum of all the internal angles should be 180 degrees. Angle E is 90 degrees, therefore sum of angle P and angle D should be 90 degrees. But that means that each of those angles have to be less than 90 degrees. So this angle alpha here has to be less than 90 degrees. But we know that point P lays outside all four circles. But that means that angle beta should also be less than 90 degrees. Angle gamma should be less than 90 degrees. And angle delta should be less than 90 degrees. And now what we're going to do, we're going to add all these four inequalities. And we get the sum of all these four angles should be strictly less than 360 degrees. Well, but that's impossible because sum of all these four angles should be exactly 360 degrees. And now we have it. We prove that such point P cannot exist, a point that sits outside of all four circles. Therefore, at least one circle should cover the point P. So now we prove that everything inside of a convex quadrilateral is covered by four circles. And the question to you is, what's going to happen if we have a pentagon, hexagon, heptagon? Also, we show that in quadrilateral, point P has to be covered at least by one circle. But is it possible to have a point P that is covered by all four circles? What do you think? If you have any ideas, leave a comment.